Jordan form is not just a dramatic way to prove that 1, 2, 3 keeps going. Today we use it to compute e to the a, and then preview why this matters for systems of ODE. So yes, the blocks finally do something useful. A rare career advancement for small squares. If f is complex analytic, we can define f of a by replacing z powers with a powers in the power series. If complex analytic feels like a future headache, keep only the special case f of z equals e to the z in your pocket. For the exponential, e to the a means I plus a squared over 2 factorial. And so on. Infinite series. Because apparently finite notation was too emotionally stable. If a equals pjp inverse, then a times to the k equals pj to the kp inverse. So f of a equals pf of jp inverse. The hard part moves to f of j. And j is built from Jordan blocks. This is why we bothered proving the theorem instead of merely decorating matrices with boxes. A Jordan block is lambda I plus a nilpotent shift n. The nilpotent part eventually becomes 0, so the power series stops inside each block. That is the secret behind the giant formula for f of a Jordan block. Derivatives appear because the nilpotent part acts like a finite Taylor expansion. For a 2x2 Jordan block, the formula is especially clean. The diagonal gets f of lambda, and the superdiagonal gets f prime of lambda. Calculus sneaks into linear algebra through one tiny superdiagonal entry. Very discreet, like an elephant in a library. Now compute e to the a for this matrix A. This A is already in Jordan form. A 2x2 block with eigenvalue 1. And a 1x1 block with eigenvalue 2. Yes, choosing a matrix already in Jordan form is allowed. This is a toy example, not a hostage negotiation. For the 2x2 block, write j as I plus n. Here n squared is 0, so e to the n is just I plus n. Since I and n commute, e to the j equals e times e to the n. The nilpotent part creates the off-diagonal e. That tiny one above the diagonal grew into a tiny e. Nature is healing. Allegedly. So the exponential of the 2x2 block is e, 0, e. The scalar block 2 simply becomes e squared. Putting the blocks back together gives e to the a. For differential equations, we usually need e to the at, not just e to the a. That means replace the eigenvalue 1 by t. And the nilpotent off-diagonal contributes the factor te to the t. The 2 eigenvalue block contributes e to the 2t. The formula is compact, which is suspicious but legal. In future ODE videos, we will see a linear system looks like dy by dt equals ay. With column vectors, the solution is y of t equals e to the at times c, where c is the initial vector. If someone writes c times e to the at, they are using row vectors or starting a convention war. Both are historically common mistakes. Using the e to the at we just computed, multiply by the initial vector c. The solution is y1 equals c1 plus tc2 times e to the t, y2 equals c2 e to the t, and y3 equals c3 e to the 2t. In component form, this system says y1 prime equals y1 plus y2. y2 prime equals y2, and y3 prime equals 2y3. The repeated eigenvalue with a Jordan block is exactly why the te to the t term appears. So Jordan form is not just classification. It predicts the shape of solutions. A shocking outbreak of usefulness. The takeaway is, Jordan form turns analytic functions of matrices into functions of Jordan blocks. For matrix exponentials, nilpotent parts create polynomial factors like t, and eigenvalues create exponential factors like e to the lambda t. That is why Jordan form shows up in systems of ODE. The blocks do not merely sit there looking official. They calculate,